Hi, let's take a look at this curved beams example. This time we have a circular ring and we're asked to calculate the stresses on points A and point B. Then we have all the data here. So this ring is affected by a force of 25 kilonewtons just here. And we have a mean diameter of the ring about, well, is 160 millimeters. And the shaded section that I need to investigate has a diameter of 80 millimeters. So it's a round section. Let's remember that this can be a ring, but the section could be different from a circular section. And this is important to know because, as I mentioned in the previous video, or to explain the exercise of curved beams, it is important to know the section because there are certain parameters that depend on the section. Great. Let's continue. One of the things to notice is that the section, if you wanted to, okay, let me get ahead a little bit. So I know that to utilize the Winkler-Bach theory, I need to know what's the section parameter represented by h squared. I called it h2 in the previous video, but no, it is, well, I will call it h squared, h2. Sorry about that. But in this case, if I wanted to calculate or derivate the formula for h squared, I would need to start by defining certain variables or certain parameters on the section. And this is the way that you can do it if you choose to kind of calculate or derivate the formula for h squared. In this case, most of these values are tabulated, meaning that you just you don't need to do it from scratch. I just showed you how to do it with the square section, but most of them are already done, calculated, so you have the benefit to use it without being or needing to calculate everything. Great. So now we have that in these 2 points, I'm going to have 2 different types of stresses. In point A, I can see, because of how the problem is set up, that I'm going to have a compressive stress. And according to the Winkler-Bach theory, compressive stress caused by the moment on that area is going to be defined under this, or using this formula here. Now in point B, it's also pretty obvious that I'm going to have a tensile stress, and that's going to be defined also with this formula here. Let's remember that these 2 formulas are the same. The only thing is that they are rearranged, so I can take D1 and D2 as positive numbers, meaning that I don't have to kind of be aware or pay too much attention to if what's the coordinate system I'm using, meaning that if it goes up is positive, or if it goes down is negative. So I will explain that later. Now the section parameter is represented, or is in function of the diameter of the section of the part, and also in function of the radius of curvature, which we don't have at the moment. We have the diameter of the whole ring. However, that diameter is not the radius of curvature. Let's get rid of the area because that's an easy one. And then let's come down. Let's come back again to the radius of curvature. The radius of curvature is going to be represented for the circular section as kind of the sum of the 2 radii. Kind of we have the diameter or the radius of the circular ring, and then we have the radius of the section. That's going to give me the radius of curvature. Now this is when I come back again to D1 and D2. In this case, D1 and D2, we saw, or as we saw in the square shape section of the previous example, that this is going to be the measure, or how much should I run from this point to this point here, or how much should I come from this point to this point here. So again, in order not to use negative or positive, I want to use positive numbers all the time. So that's why I rearranged the formulas in this sort. Okay, but this is not it's not that I have all the ingredients here. So I have the area, I have the radius of curvature, I have h squared, I have d1 and d2. So I know that, what's the moment applied, to this section there. So I need to calculate that, but also I need to be aware that this force here is not applied on the section, it's applied, away from the section. So when I want to understand what's happening in the shaded section conformed by the points A to B, then I know that when I move or translate this vertical force to here, this is going to be, it's going to bring me a force plus a moment here. So that's going to be the consequence of representing this force in another place or another point. If I substitute the values for H2, I'm going to find that is going to be this one, 422 millimeters square millimeters. And let's see, if I have all these components, there is something interesting to the formula for stress. In both cases, for the stress in point A and the stress in point B, it is not only the stress because of the moment caused by the force that I have to take into consideration there. It is pretty obvious that this part here of both equations represents the stress caused by a moment applied to the section, and this moment comes from the force P. We will see how to calculate it. However, as I mentioned that, when I start studying this section here, we change the color, and I kind of translate this force, the effect of this force of 25 kilonewtons that is presented here into this part. This is going to bring not only the force, but it's also going to bring a moment. Now, this moment is the one that I'm going to use for the Winkler-Bach theory, meaning that this one moment is the one that I'm going to introduce here. However, as I'm seeing that I have a force applied on that section, on that area, this force is going to cause a stress. And in this case, for either point A and point B, the stress is going to be a compressive stress. That's why this appears here. So let's remember that one thing is that, that they ask us that to apply the Winkler-Bach theory. And another thing is that they ask us to calculate the stresses. So if I have to calculate the stresses in points A and point B, then it means that I have to consider all possible causes for stresses. And I'm going to have moment, and as the moment is applied on a round section, a curved section, then I have to apply the Winkler-Bach theory. And also I have a straight force applied on the section that's also going to cause a stress. That's why these two terms are appearing here. So the appearance of this term doesn't have anything to do with the Winkler-Bach theory. It has to do that there is a stress caused by this force. Well, let me clean out a little bit here. Then the moment is going to be equal to the force times the radius of curvature. Then if I substitute everything into my formulas in here, and in here, I'm going to have that the stress in A, which is a compressive stress, is equal to minus 0.084 kilonewtons per square millimeter. And in the same on the other point, on point B, I'm going to find that the stress is 0.042 kilonewtons per square millimeters. Now, these kind of units are a little bit messed up, so let's put it, in units more sound for us. And here is when I will transform these, kilonewtons per square millimeters into a more conventional stress unit representation. In this case, I will have as compression minus 84 megapascals for point A, and I will have 42 megapascals in tension for point B. And again, be careful of this. This doesn't have to do anything with the Winkler-Bach theory. It has to do that this force causes a stress in the sections of the whole uh, ring that we're studying at the moment. But this part is how to calculate the stress caused by a moment in a curved beam. And well, and this is it. This is the procedure to solve these type of problems. Thanks.